Look closely at this galaxy for a moment, because according to everything we thought we knew about the universe, it should not exist. Its spiral arms are enormous, perfectly organized, and filled with dense clusters of stars that appear mature and stable. Structures like this normally require billions of years to develop, yet the James Webb Space Telescope has just discovered one sitting almost at the very edge of cosmic time. According to its distance, this galaxy had only about 300 million years to grow. To put that in perspective, that is less time than it can take for a single generation of stars to fully evolve in our own galaxy. And yet, the structure is already complete, massive, and surprisingly complex. Even more unsettling is the fact that it is not alone. For nearly a century, scientists have treated the Big Bang as settled science. The universe expands, the mathematics fits, and the cosmic microwave background appear to confirm the entire story. For decades, the model seemed closed, as if the case had already been solved. But this year something changed. New observations returned from multiple observatories, and 3 discoveries arrived almost simultaneously. Each one alone would have been surprising. Together, they forced cosmologists to reconsider ideas that have guided physics for generations. The first discovery involves galaxies that appear far older than the universe should allow. The second concerns black holes that somehow grew to impossible sizes far too early in cosmic history. And the third discovery involves a measurement so precise that it seems to break the timeline of the universe itself. When scientists connect these 3 puzzles, they point toward the conclusion that once sounded unthinkable, the Big Bang might not have been the true beginning of everything. If you have been following our investigations, you know we often focus on strange objects moving through our cosmic neighborhood. But while attention was focused on nearby anomalies, cosmologists were quietly documenting something far more profound, nearly 13 billion light-years away. The evidence was not speculation or theory. It was data coming directly from powerful instruments like the Planck satellite and large-scale surveys such as the Dark Energy Spectroscopic Instrument. To understand why these discoveries are so shocking, we need to begin with a single number that defines our entire cosmic history: 13.8 billion years. That number represents the estimated age of the universe, calculated by measuring how quickly space itself is expanding. If you run that expansion backward through time, all matter and energy eventually converge to a single origin point known as the Big Bang. Everything in cosmology operates inside that 13.8 billion year window. Galaxy formation, star formation, the creation of elements, the entire structure of the universe depends on it. But now, the James Webb Telescope is observing galaxies that appear 2 billion years old inside a universe that was only 300 million years old at the time, and that is where the real problem begins. One of the most striking examples is a distant galaxy known as JADES GS-Z140. Astronomers estimate that it formed only 280 million years after the Big Bang. When researchers analyzed the faint light coming from this galaxy, they discovered something astonishing inside its spectrum. Elements such as carbon, oxygen, and nitrogen. These elements are not produced during the Big Bang itself. They are forged deep inside stars and then scattered across space when those stars explode as supernovae. That means this galaxy had enough time to create its first generation of stars, allow them to live out their lives, explode, spread heavier elements through space, and then form an entirely new generation of stars enriched with those elements. All of that had to happen within 280 million years. Here is where the timeline starts to break. Massive stars take roughly 50 million years before they explode as supernovae. The very first generation of stars in the universe did not ignite until about 100 million years after the Big Bang. That leaves only 180 million years for this galaxy to complete a full cycle of star birth, stellar death, and chemical enrichment. After subtracting the time required for those first stars to form and explode, there would be only about 80 million years remaining to build the mature galactic structure that the James Webb Telescope is now observing. The numbers simply do not close. The math refuses to cooperate. Even more troubling is that this is not just one strange object. In February 2025, researchers at the University of Cambridge studied 12 massive galaxies that existed within the first 500 million years of cosmic history. Every one of them appeared far more developed than expected. Their combined stellar mass was equivalent to roughly 10 billion suns. Astrophysicist Ehud van Dokkum described these objects with a phrase that quickly spread through the scientific community: universe breakers. Because if the observations are correct, then something fundamental is wrong. Either star formation worked dramatically faster in the early universe than any current model predicts, or the cosmic timeline itself is incorrect. And the mystery deepens when scientists examine what lies inside these early galaxies, because within many of them are enormous supermassive black holes that should not exist yet either. One example is the galaxy cluster Phoenix A, which contains a black hole estimated at 100 billion times the mass of our Sun. We observe Phoenix A as it existed 8 billion years ago, meaning that this monstrous object formed within the first 6 billion years of the universe under standard growth models. That should be impossible. Black holes grow by pulling in matter around them, but physics places strict limits on how fast that growth can occur. Yet somehow these cosmic giants appeared far earlier than theory allows. And once scientists began searching for them with new telescopes, they found dozens more. The James Webb Space Telescope has now revealed multiple supermassive black holes that already existed within the first billion years after the Big Bang, many with masses exceeding 1 billion suns. These objects appeared when the universe was less than 10% of its current age. According to standard astrophysical models, that growth rate should not be possible. The reason comes from a physical boundary known as the Eddington limit. As matter falls into a black hole, it heats up and releases enormous radiation. That radiation pushes outward against incoming material. Once a black hole reaches the Eddington limit, the outward pressure prevents it from growing any faster. If the limit is exceeded, radiation should blow the surrounding gas away and halt further growth. So how did these ancient black holes become so enormous so quickly? Scientists have proposed three possible explanations. The first possibility is that the black holes began unusually large, forming through something called direct collapse, where enormous clouds of gas collapse directly into black holes with masses of 100,000 suns or more. The problem is that the conditions required for this process are extremely rare. They simply cannot explain the number of giant black holes that telescopes are now detecting. The second possibility is that black holes somehow grew faster than physics normally allows through super Eddington accretion. In theory, certain extreme environments might allow matter to fall in faster than the Eddington limit predicts. But this idea remains highly speculative and has not been confirmed observationally. The third possibility is far more radical. These black holes might not originate from our cosmic cycle at all. Instead, they could be remnants left behind from a previous universe. Before jumping to that idea, however, there is another puzzle that may be even more serious. It involves the expansion rate of the universe itself. Astronomers have two different ways to measure how fast space is expanding, and both methods are incredibly precise. Yet, when scientists compare the results, they do not match. The first method studies the cosmic microwave background, the faint radiation left over from the early universe. Measurements from the Planck satellite show that the universe expands at roughly 67.4 kilometers per second per megaparsec. The second method uses exploding stars, known as type Ia supernovae, as cosmic distance markers. That method produces a higher value of about 73.2 kilometers per second per megaparsec. The difference between these numbers is small, but extremely significant, about 8.6%. In cosmology, where measurements reach extraordinary levels of precision, such a disagreement is enormous. This discrepancy has become known as the Hubble Tension, and the chances that it is simply random measurement error are estimated at less than 1 in a million. And instead of disappearing with better data, the tension keeps getting stronger. In March 2025, Nobel Prize-winning astrophysicist Adam Rees released new measurements that reduced the uncertainty even further. Instead of solving the disagreement, the improved data made it clearer that the two expansion measurements truly conflict. If both are correct, something in our understanding of the universe must be missing. One possibility is that the mysterious force known as dark energy is not constant after all. For decades, the standard cosmological model has assumed that dark energy behaves like Einstein's cosmological constant, remaining unchanged throughout cosmic history. But new observations are beginning to challenge that assumption. The Dark Energy Spectroscopic Instrument, or DESI, spent 3 years mapping the positions of 40 million galaxies, measuring their distances and redshifts with unprecedented precision. When the collaboration released its results in April 2025, the conclusions surprised many cosmologists. The data suggests that dark energy may actually be weakening over time, declining by roughly 5% during the past 10 billion years. If dark energy is evolving, then the expansion of the universe may not follow the simple pattern scientists once believed. The expansion could slow, change direction, or even reverse in the distant future. But it also means the expansion rate in the early universe may have been different from what current models assume. And that might explain the mysterious 8.6% gap in the Hubble tension. Yet another surprise appeared when astronomer Alexia Lopez identified an enormous cosmic structure known as the Big Ring, stretching an astonishing 4 billion light-years across. Nearby lies another structure called the Giant Arc, extending more than 3.3 billion light-years. According to the cosmological principle, the largest structures in the universe should be roughly 1 billion light-years in size. These formations are several times larger than that theoretical limit. When scientists place all these anomalies side by side, ancient galaxies that formed too quickly, black holes that grew too fast, an expansion rate that refuses to agree with itself, dark energy that may be changing, and cosmic structures larger than theory, allows the problems begin to connect, like pieces of a larger puzzle. Some researchers, including Richard Lieu, have proposed the idea of multiple mini-bangs, bursts of creation scattered across time that could explain many of these anomalies. Others, like Nobel laureate Roger Penrose, suggest that the universe may be cyclic, with each Big Bang representing a transition from a previous cosmic era rather than a true beginning. If that idea is correct, then the universe may not have a single starting point at all. Instead, it could be part of an endless sequence of expansions and rebirths stretching far beyond the limits of our current timeline. Future observations from the James Webb Telescope, DESI surveys, and new cosmological experiments will continue testing these possibilities. Either 5 separate measurements are all wrong at the same time, or the story we have told about the origin of the universe needs to change. If you found this exploration fascinating and want to follow the next discoveries reshaping our understanding of the cosmos, make sure to like the video, subscribe to the channel, and share your thoughts in the comments, because the biggest mystery in the universe might only be beginning to reveal itself.